Hey, this is David from UCR Supplemental Instruction, here to talk to you about Physics 40B, and this time we'll be talking about the principle of superposition, as it applies to waves, that is. So first off, the actual principle itself is really fundamentally pretty simple. And so what it means is that when two waves overlap, or when they occupy the same space, their displacements add together. So I'm going to show what that looks like in a couple different ways. At the top here, we have what's sort of like an implied 3D graph. We have a sort of rippling wave like you might see if you drop a rock in a pond, or maybe from sound waves. And below, we'll be looking at just some transverse waves. So starting off with the transverse waves, let's just draw some in and we'll see what happens. So for the first one, we'll just draw something like this. And for the second one, I'm going to draw something that is essentially the same thing. All right, so let's pretend that these two waves are coming from sources that are right next to each other and in the same direction. So again, going to the principle of superposition, how is that going to affect the resultant wave? So if they're right on top of each other, and like we said, their displacements add together, let's see, we'll do the resultant in green. And we're sort of just eyeballing the displacement. It's about this height. Now, if we add them together and they're essentially the same wave, well, 1 + 1 is 2, and you'll get something that is roughly twice, very roughly, twice as tall. So the displacement here would be, if we just take the maximum, let's see, at a point, we'll pick right here on both of these lines. This is the maximum, and we'll say that the displacement here is equivalent to d. Then at this point, at the same point on our other graph, because again, we're adding, the total displacement is equal to twice that. Right, so pretty simple. But of course, things can get a lot more complicated than putting the same wave on itself. So looking above this, you can see something that is already a little bit more complicated. So first off, let's put some terms on these. So this might come later in the chapter, but when you have two waves that add to each other like this, and the maximum amplitude becomes the new maximum amplitude twice this, we refer to this as constructive interference. Let me type that out. So interference, because these two waves are right on top of each other interfering. Constructive, because they're building on one another. So let's adjust this a little bit and see how things change. First thing that I want to do is just change the phase a little bit. So we'll say it goes to here, and we'll measure this at the same point in time, or same point in distance along this wave, and I'll just draw out the continuation of this, just for completeness. So we can see that where one wave is high, the other wave is low. So as you probably expected, we're not going to get the same wave out of it. Let's see instead what happens. Going back to the same color. Right, so if we're adding these two together, and we pick the same point D, well, if this is positive D and this is negative D, positive 1 plus negative 1 is 0. So between those 2 points, we'll be at 0. So we can actually just move this down. And we don't know fully what the waves look like, so we can just try another point. Let's try, let's look right here, but at the node of these two waves. Well, these would both be 0 displacement, so 0 plus 0 is still 0, and the wave is still 0. So if we take that point, it also plots to 0. As you can imagine, if we plot the trough of this wave and the peak of this wave, well, it's the same thing as the previous peak and trough. Negative 1 plus 1 is still 0. So at any point, if we add the displacements, you get nothing. And so for that reason, the wave is also just nothing. It's been pretty much flattened out entirely. And so this is what we would refer to as destructive interference. Something so simple, it's just taking two waves and overlaying them just like this. We can get nothing out of it. And that's how sound canceling headphones work. Any outside sources, they produce a wave, such as this red wave, that'll cancel them out. And they're pretty effective at that, as you may have firsthand experience with. So let's continue to this implied 3D plot up here. So if we were to take a line that just connects the two centers here, say right there, if we were to analyze the waves along this line, we would get something that looked exactly like these 2D plots, just viewed from a different angle. And so what's meant here is that each of these rings is the peak of a wave, so, or an antinode, you could say. And so we'll probably move on to that later in the week. And so somewhere like right here, this is a peak, this is a peak, and between these two waves, we will have troughs, so something like this. And so in the spaces right in the middle between these, the wave's at its lowest point, and on the lines, it's at its highest point. So analyzing from this point of view, no longer just looking at the wave along a line, of course, they're radiating out in the circular direction. So again, going to this idea of constructive and destructive interference, where is it occurring? So as we saw, when a peak lines up with another peak, we have constructive interference, and when a peak lines up with a trough, we have destructive interference. So again, just looking at this graph and the way it's plotted, so one of these lines being a peak, when it lines up with another peak, such as right here, we'll have constructive interference, and we'll get twice the amplitude, or twice the displacement rather. And same for any of these other points where the lines overlap. And as you can tell, they're not just along this line too. We have points up here, we have a point down here, and several other points. Okay, so what about destructive interference? Well, you saw with this wave, we had to change the phase to get destructive interference entirely. On the other end, having them line up, we had constructive interference throughout. So with this wave, and again, we're not changing the waves at all, they're actually points of constructive and destructive interference at the same time. So a point of constructive interference would be where a node lines up with, or a trough rather, lines up with the peak. So if we were to say that the spaces between these are troughs, then where a trough lines up with the peak would be, let's say, right here. So at the point where that blue line is directly between these two red lines, there's destructive interference. And to be clear, another way you could plot this is where the red lines, or the color lines themselves, are both peaks and troughs, and instead the space between them are nodes. But for now, what I'm going to say is that the space between them is troughs, so just be prepared for that. It's not always going to be the same. So, but also by that same token, where a trough meets a trough, that's still constructive interference, and we can still see that somewhere like right here, at this spot between these two. I'm not placing these perfectly, but that's the idea. So if we were to look at this analytically and not graphically, we would be using the wave model equation that we've seen before, d of x of t equals the amplitude times the sine of the wave number times position, position along this s-axis. Here it's written as s, not x. Same thing though. Plus omega t, omega being the angular frequency, and then plus the phase constant phi. So if we were to solve for these things, again, what we've been doing the whole time is adding the displacements. So depending on the parameters you're given, time, position, phase constant, etc., you can calculate the displacement at a point, and the point you do it is really particular, as you can see here, because it's different at various points, and so is the time. Because if these two waves are moving at a different speed, not something that happened in terms of sound, but there's a lot of possibilities. If we wait a second, then this wave will move and the points of interference will change. And of course, you don't just have to be looking for a point of interference. You could just be looking for the resultant displacement at any given point. Though typically these are the points of interest. So again, just doing this analytically, plug things in, understand which direction waves are moving. That's pretty important. If I didn't say in the beginning, it was implied that both of these waves that we started with are moving in the same direction from left to right. So just plugging things in, and this is essentially what you're doing. I find it helpful to graph things out sometimes, just so you can see which direction things are going. But that's really all there is to it. So I hope you learned something, and I'll see you soon.